Okay, hi everyone. Vidich here. Uh, Today I want to talk about a correlation, just to continue off on what we were doing last class with scatter plots. So so correlation is basically quantifying the strength of an association. So when we talk about scatter plots, we talked about direction, positive or negative, form, linear or nonlinear, and then strength. We had weak, none, strong, fairly strong. Now we're going to actually give this a number here. In correlation, the coefficient of correlation that we use is R. So R, and R can be anywhere from -1 all the way to +1, and we're going to see why that is in a second. So let's look at our first example here. From your textbook, you have some students here, and we're looking at the association of their heights in inches and their weight in pounds. Okay, and clearly there's first of all, it's linear. That's important. Okay, it's fairly linear. There's positive direction. It looks fairly strong. All the points are sort of close together. There is one kind of unusual point here, and that might be an outlier, and we can look for that. Investigate that a little bit further. But in general, so how do we get a value for the strength of the correlation here? And this is what we're going to do today. So the equation for the correlation is this. So we have, and I'll just give it to you right away, and we can talk about it a little bit. So it's R equals, and then it's the sum of the Z scores for X times the Z scores. Let me put a little thing here. Z scores for Y. And then again, we're going to divide by the number of points. And again, not exactly by the number of points, but by n minus 1. And again, I'm going to leave you sort of in the dark here as to why it's n minus 1. We'll get to that in future lessons. But the most simplest answer is gives us a better approximation when we have smaller data samples, okay, or smaller number of observations. Okay, so what are we doing here, and why do we have Z scores? So here we go. So okay, the reason we put the X and Y variables, the data in as a Z score is because the Z scores have no scale, or have no units, I should say. Okay, they're on the same scale. If you look here, we have inches, and the scales, goes to from about 64 to 76, or whatever, that 60 to 76, and here we have pounds, and that's a completely different scale. So if we multiply those two variables together, we get a crazy number that won't be relevant to another example if we're not using inches and weights. So we want to standardize everything, and Z scores are they're equal across the board. Doesn't matter what variable you're looking at. Okay, so let's first so what we do in the second picture over here is we take all those points, all the observations from the above, and we turn them into Z scores. Okay, and you'll notice the shape is a little bit different. Let's look at this one. Okay, the shape is a little bit different, and again, the reason they're different is because of the scale. Okay, the scale just changed. That's it. Okay, the correlation is the same. The number is not gonna change here, but this is actually a fairer representation of what the data points look like, because now they're on the same scale. Okay, and the origin. Okay, the origin in this case makes a lot of sense. This is the mean for the heights, and the mean for the weights. So that's what the origin represents in this case. Okay, all the positive, or I should say all the green points here support a positive correlation. So all of these ones support a positive correlation. That's because if you have a Z score of look at this one here, maybe this point here, the Z score for the heights would be, I don't know, 2, and a Z score for the what is it? The weights would be, I don't know, 1.8. So when we multiply those two together, when we multiply the z-score for x times the z-score for y, you get a positive number. Same thing down here, right? If we multiply a negative z-score times a negative z-score for weights, you get a positive number. So all the green points support a correlation, support a positive correlation. Okay. On the other hand, all the red points, you're going to get a negative answer. Okay. These people, okay, these individuals that are in red here, they're not fitting the model, or they're not helping out our correlation here. So again, if we looked at the correlation values, they go from -1 to +1, meaning that 1 is every point would be on a, let me draw an imaginary best fit line here, which again we're going to learn how to do in chapter 8, but eyeballing it would look something like this. And if this was a perfect correlation of 1, every single point would be on that line. Okay, so that's why, and if it was a negative correlation, then it would go this way. Ooh, that's a terrible straight line. Okay, and all the red points would support a negative correlation. Okay, so in this case, you can see this as a battle between the red and the green here. Okay, the green points are supporting a positive correlation, while the red points are going against that. Okay, they're the students in the class who's are counterintuitive to our positive correlation here. Okay, in other words, these kids here, okay, they have their height is, they're short, but their weight is high. Like this person here, he's -1 standard deviation for height, but he's almost 2 for weight. So you can imagine some short chubby kid here. Okay, this is the short chubby kid over here. All right. Yeah. Okay. So let's so once we get the z-scores, again, we'll get let's go back to our equation. Let me just rewrite it again. Okay. So z-scores, or sorry, the correlation equals the sum of all these products. So we have a z-score for x times the z-scores for y, and then to get an average here, you divide by the number of points. In this case, it's going to be n-1. Okay, so that is how you calculate the coefficient of correlation. Okay, and the answer is always going to be between -1 and 1. Okay, if we left it in inches and pounds, okay, it would be a crazy number that would only make sense for inches and pounds, right? So that's why you want to standardize everything into z-scores. All right, now we're not going to do this by hand, okay? The calculator does this for you, and this is what I'm going to get to in a few examples in a second here. But this would take forever again, right? You have 1,000 points here, right? Not 1,000, but you have about 50 dots there. That's a lot of math for no good reason here. Okay, and imagine trying to convert all of these points into z-scores. After about 5, your head would explode. Okay, so again, moving on here. Okay, before I do a few examples here, I just want to talk about a couple conditions here. Okay, a couple assumptions we have to make before we start calculating the correlation coefficient. Okay, again, the correlation coefficient measures the strengths. It quantifies the strength of an association between two variables. Now, what's important here is that those variables are quantitative. You can't do this on with categorical data. Okay, it has to be. So your 3 conditions. Okay, we have conditions here. Okay, your 3 conditions are: 1, okay, you have to have quantitative data. Quantitative data. Okay, 2, it has to be linear. Okay, you have to have a linear. Your form of your scatter plot has to be linear. If you have something like this, okay, where it's sort of sloping up, curving up, it won't work. Okay, there's things we can do to this to make it work, but it has to be linear. This only works for linear models. And then finally, 3 is outliers. So even if you have a fairly strong fairly strong scatter plot here, fairly strong association. Even if you have one, outlier here, that's going to pull the line. So instead of having the line like this, it's going to completely pull the line towards that outlier. So you have to check for those three conditions. If your example violates any of these conditions, you cannot do the coefficient. You cannot determine the coefficient of correlation. Okay. All right. Last thing before I do a couple examples here. So if the important is a huge section in your text that says, and you heard this over and over in your life, correlation does not equal causation. Okay, correlation does not equal causation, and that is, most people jump to the conclusion thinking that, okay, as soon as you have some sort of an association, well, this variable causes that variable. And the funny example in the book was you had the population of a town. I can't remember where the variables were, but it doesn't matter. So the number of people in a town, I think that was actually probably makes sense if that was on the y-axis. So let me just cross it out. Okay, so number of people versus the number of storks. Okay, and I think there was, the scatter plot looked very, very, very appealing, right? You had something like, let me get a little fatter pen here. You had something, as the number of storks, increased, the population of the town also increased. Well, can we come to the conclusion that storks bring babies? Probably not, right? This association, I think it was above 0.9, which would suggest that it's a very strong association, very strong, a high correlation coefficient. But again, just because we have that doesn't mean that one causes another. All right, and I think the explanation was that storks they nested on the roofs of the houses. So as there were more people in the town, there was more roofs, and that attracted more storks. Okay, so that's what's called a lurking variable. Okay, a lurking variable is a third variable that explains both of the other two variables. I think at the beginning of the year I gave you that example where that kid says there's less skateboarding accidents in the winter, so I'm going to skateboard down the popsicle precipice, right? But again, the reason is there's less skating accidents and less skateboarding accidents in the winter because people just don't skateboard in the colder months. Okay, all right. Okay, so let's do a couple examples here from your book. I'll start with number 40. Okay, vehicle weights, and it says here the Minnesota Department of Transportation hoped that they could measure the weights of big trucks without actually stopping the vehicles by using a newly developed weigh in motion scale. Sounds like a little bit of magic to me. Okay, to see if the new device was accurate, they conducted a calibration test. They weighted several stop trucks, static weight, okay, on a scale, and assumed that this was the correct, that was the correct weight. Then they weighed the trucks again while they were moving to see how well the new scale could estimate the actual weight. Okay, well, all right, the data are given in the table on the next page. Okay, so we have the weights in pounds here, and let's see what the first question says. Make a scatter plot of these data. Okay, so again, I'm not going to waste your time here. So I already put this in my calculator under the motion weight in list 1, and the static weight in list 2. So in this case, the response variable, or the y-axis variable, will be the static weight, and I guess the explanatory variable would be the weight in motion. So we'll see how the weight in motion explains the real weight. Okay, so again, to make a scatter plot, second function, stat plot, we'll go to the first one, and I'm going to turn it on, and the scatter plot is the first one. Okay, and here again you have the the default is L1 and L2. You can choose which type of if you want a square for each point or a plus or a dot, whatever. So again, zoom 9. Okay, and there it is. Okay, so again on the x-axis we have the weight. We have the weight in motion. Okay, while the trucks are in motion, and on the y-axis we have the static weight. Okay, so ideally, obviously, we want it to be a straight one-to-one representation here. So if the static weight is 27.9 thousand pounds, we want the weight in motion to be 27.9 thousand pounds. But is this how good is the correlation here? Well, in this case, you want it to be pretty close to 1, because you want to be fairly accurate here, right? This is there's still trucks, right? Whether they're moving or they're stopping, their weight should be the same. So there's a scatter plot. And let's go to B here. It says describe the direction, form, and strength of the plot. Well, the direction is positive. The form is linear. Okay, clearly linear here. And the strength of the plot, well, I'd say that's pretty strong. Okay, pretty strong. So write a few sentences telling what the plot says about the data. And again, so here's the point. Key point here: the sentences should be about weighing trucks, not about scatter plots. So I guess my best sentence here would probably be something like, okay, the weigh in motion scale, is fairly useful at predicting the static weight for trucks. Maybe we can look at the individual data here, and we can look at sort of an overall pattern. And what I do see is that the last 2 points they vary quite a bit from that sort of linear pattern, right? And if I look on my table here, the last 2 points here, okay, that's I have the static weight's 33 here, and then I have 35, and then 35. The truck that's 35 is 40. So that's quite a bit of a quite a bit of a difference compared to the other points. The other ones are all pretty close. 30 to 31. This one's kind of underweight. So the scale is fairly consistent, up until the last 2 points, and then it sort of gives a pretty high estimates. So you can mention that as well. Okay, what's the next? Okay, so find the correlation. Okay, so let's find the actual number here. So again, we're not going to do this by hand. Your calculator does this for you. So here we go. So hit hit stat, and we're going to go to calculate, and now we're going to go down to 8, and 8 is your linear regression. So it's going to calculate the coefficient of correlation for you. So again, the default is L1. L2 on your calculator, you might have to do the L1 comma L2, okay, to tell it, and then enter. So we'll go down to calculate here. Okay, and all right, now if your calculator does this, and my computer one seems to be resetting itself all the time. So if it's the first time you've done this, you're only going to get these 3 values. But if you want to get more values, and more importantly, the correlation coefficient, you got to go, and you only have to do this once. Okay, so go second function, catalog, and go down to diagnostics. Okay, diagnostics on. Okay, hit diagnostics on. Okay, and now when we do stat calc 8. Okay, list 1, list 2, calculate. Okay, so now you get your the equation of your line, which is y equals a plus bx, and the b is the slope, y is your y variable, your response variable, x is your, in our case, the static weight of the trucks. Okay, the one we're interested in is an R down here. So R equals 0.965. Okay, and again, that is a very strong correlation, as we would expect it to be if their tool is this measuring tool, their weigh in motion tool is going to work. Okay, you want it to be close to 1. All right, let's look at E here. So if the trucks were weighed in kilograms, how would this change the correlation? Well, it wouldn't. As a matter of fact, it wouldn't change. It wouldn't change it at all. Okay, because that's a linear transformation. So just adding or multiplying our data values by the same coefficients does not change anything. And let me show you quickly how, just to prove that to you. So let's get out of here. So what I'm going to do is this. So I'm going to take my list 1, and I'm going to multiply it by 2.2. So change it into, or I should divide by 2.2 because we're already in pounds. So I'm going to go to kilograms. So divide by 2. And I'm going to store those answers. So go store. I'm going to store those guys into L3, okay? And I'm going to take my L2 values and divide those by 2.2 and store that into L4. And I should probably put a decimal in here. Okay, there we go. So now if I look at my lists here, stat, edit, okay, you can see that 26, the weights in pounds, and then L3 is the weights in, so there's a quick way of doing that, a little shortcut. And so if I did regression line, stat, calc, the regression line, oh, I messed up again. Okay, stat, calc 8. Now we're going to go L3, comma, L4, calculate this guy, and it should be the same. Yeah, there it is. Okay, 0.965. Okay, so that changing it doesn't, changing it to kilograms doesn't do anything. Okay, so let's just look at this. So do any points deviate from the overall pattern? So we already kind of talked about that. These last two deviate. What does the plot say about the possible recalibration of the weigh in motion scale? Well, again, any answer is pretty good here as long as you mention those 2 points. You can say something like, the scale doesn't seem to work as well when the weights, when the weights are high. In this case, over 30, 33 or 35 here. Okay. So that's that one. Okay, let's move on to the next one. Number 42 here. All right, so let me pause this and I'm going to put the numbers in. Actually, no, I'm going to make one good point here. So let me. So let's see. So the flights. The number of flights by U.S. airlines has grown rapidly. Okay, as we expect it to be. Any company tends to grow. Okay, if it's doing well. So here are the numbers of flights flown in each year from 95 to 2005. Find the correlation of flights with the year. Okay, make a scatter plot and describe the trend. Note, again, trend. So anytime we plot something against time, it's called a trend. Note 2 reasons that the correlation you found. Okay, we'll get there. All right, let me put these data in my stat edit. Let me go over to list 5. Okay, now, instead of typing in 1995, I can just go 0 to 0 to 10, or what is this? 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, 11 points. So I'm gonna go 1, 2, 3. I'm gonna pause this. Okay, so I put in the years 1 to 11, representing each of those years, and now I'm gonna put the flights. And now here's a little tip for you. Okay, now on the AP exam, you're most likely not going to be given this type of data where it takes you a long time to input all the data into your calculator. You're wasting quite a bit of time. But just, a little shortcut here. And I did this with both numbers here, and the correlation is very close. So what I'm going to do is I'm going to, basically knock off the last 3 digits here, okay? Because I don't think they're very significant. And I'm going to just input into my calculator the first 4 digits. And doing this both ways, okay, your 4th decimal place of your coefficient of correlation changes. The first 3 will be the same. So if you want to save some time here, the last three digits are not going to take a big factors. So you can truncate those off. Okay, so let's go 5,327 327, and again I'll pause this. Make sure you round up if you are going to do this. Round the fourth digit up. Okay. Okay, so I got all my number of flights in list 6. Okay, find the correlation of flights with the year, and then B is make a scatter plot and describe the trend. I'm going to do B first because I think that's a natural way of doing this. So let me just do a scatter plot first. So second function, stat plot, and here we go. Except this time it's going to be L4 and L5. No, L5 and L6. Oh, I forgot already. Okay, let me check. Yeah, L5 and L6. So list 5 and list 6. Okay, and if you want to get cute here, and you can name your lists, to whatever you can actually put the letters year and flights and to name your list, and you can pull up all the lists from second function here. There's all the lists there. You can pull them up, and any one you create will be in there. Okay, back to this thing. Okay, zoom 9. I have an error, okay, and I'm guessing my error is that I did not have a different number of data points in my data table, so I didn't enter something correctly. Let me just double check that this is correct. Oh no, here's the error. I did L5 and L2, so I need to do L6. Okay, there it is, L6. Now I go zoom. Oh, I got this annoying thing again, so clear this. Let me go up here, zoom. No, zoom 9. Okay, yeah, there it is. All right, so okay, this one's a little bit interesting. I noticed a linear pattern for the first few, and then sort of a curving pattern for the last few. I also noticed an outlier, and if I look at my data, I see that outlier is 2002. Okay, we can talk about that in a second. So what am I? Describe the trend. Well, the trend is that the flights are increasing. The number of flights are increasing as as the years go by. Clearly, okay. So I'm not describing the scatter plot in this case. So be very specific to how you're answering this. So the trend is positive and curved. And definitely mention the outlier in 2002. Okay. All right. Let's go back to the first one. Now find the correlation. Okay. So find the correlation. Stat, calc, and it's 8. Okay. L5 and L6. That's where my data is. Calculate. Okay. What do we have here? So R equals 0.827. Okay, so pretty strong correlation. However, okay, just because we have a strong correlation doesn't mean that it's valid. Okay, and the reason it says here, probably for C here, is going to be named 2 reasons that the correlation you found in A is not suitable, not a suitable summary of strength of the association. Can you account for these violations of the conditions? Well, okay, so the two are okay. So it's curved and an outlier. Okay, so that's breaks 2 out of our 3 rules. 3 conditions. Remember, our conditions are linear, no outliers, and what's the last one? So and that our variables are quantitative. In this case, the variables are quantitative, so that one's okay. Okay, so can you account for these? So we can't use the correlation. So this this is wrong because our our models, our conditions are not met. Can you account for these violations of the conditions? I can maybe account for the outlier. 2002. That's the year after September 11, or sorry, at the end of that year. Maybe the flights went down because of September 11th. Otherwise, Maybe businesses, sometimes follow a non-linear model, right? They maybe start off slow, 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 and then they take off once business is good. Maybe that accounts for the linearity. Okay. Hopefully you got the hang of this by now. I'll see you next time.